So now I'm going to work through two problems to show you how to run a two-sample t-test. Here we have two samples of runners in heat 2 and runners in heat 5. And we want to test to see if there's a statistically different average between those two heats. So we can calculate the average for heat 2. There were 6 runners in that. And there were 7 runners in heat 5. And you can see that they're really pretty close and that their variation is almost a full second. And so we just want to test to see, are these completely different or are they statistically close? The first thing we want to do is set up our null and alternative hypothesis. Here I'm putting heat 2 first, but it doesn't really matter which heat you put first. That's only going to change the sign on your t-score. Your final conclusion should still ultimately be the same. If you put heat 2 first, we'll get that there's a negative t-score. The alternative hypothesis then is just that they're not equal, so we're still going to run a two-tailed test. We can calculate the t-score then by looking at our sample difference. So I put the heat sample for heat 2 first, and then the average for heat 5 second to be consistent with my hypothesis. And then I subtract off 0 because 0 is our hypothesized value or our hypothesized difference. We divide by the standard error then of the sampling differences. We just have one sample here, but this captures the fact that samples may vary. And so we have in here the standard deviation for heat 2, the standard deviation for heat 1. Both of those are squared, and then we divide by our sample sizes. We add those two terms up and then square root. That's going to give us a t-score of negative 0.45. So once we have that t-score, we can move on to calculating our p-value. Now, our p-value comes from the alternative hypothesis. So we said that the alternative hypothesis is that it's not equal to 0. But when we look at the probability, we want to look at the probability that we observe the sample that we do. So the value I have here is actually the sample difference. This is the difference between our two averages. We're looking at the probability that we'd observe the sample that we do given that this assumption is true. And so that's equivalent to saying, what's the probability that we see a z-score that we do, because this z-score is completely related to this sample difference. There's a one-to-one relationship. And so we can calculate this, this should be a t, this t-score or this probability using the t cumulative distribution function. If we use our calculator, what we want to enter is this formula, the t-CDF, reaching to the lower tail, so reaching to negative infinity. The upper bound is the t-score that we have. And then our degrees of freedom. Here, our degrees of freedom would be 11 because the two samples, 6 and 17, is 13 observations, minus our two parameters. That's what gives us 11. We're going to times this by 2 to get both the lower tail and the upper tail, because again, we're running a two-tailed test. That gives us a p-value of 0.66. If we use the Excel formula, we're just going to enter equals t distribution, or the t-score that we're looking at, the degrees of freedom, and then 1 to calculate the cumulative distribution function. Again, we want to times that by 2 because we're running a two-tailed test, and it will give us the same p-value. We can now move on to our conclusion, where we compare the p-value to our alpha level. Our alpha level that we determined before we implemented this problem was 0.05. So you determine the criteria, the level of evidence beforehand. Because the alpha is less than our p-value, we must fail to reject the null hypothesis. That is, our p-value is greater than alpha, so we just don't have enough evidence to say that there is a difference between the runners in these two heats. You can see in our two samples that there is a difference, but again, this is just samples, and if we were to sample more runners, we might see that the two heats actually reversed. So again, based on our sample, we just don't have enough evidence that there is a difference between these two runners. In the second problem, we're looking at how researchers wanted to investigate the size of a drinking glass and how it impacted how much people pour into that. There were two different size glasses, 17-ounce glass and a 25-ounce glass. They had 24 people use the small glass and 25 use the large glass. Again, it doesn't matter that we're using two different sample sizes. Our tests account for the difference in these sample sizes. You can see that the sample average for the large glass users is higher than the small glass users. Now, this may just be because of sampling variation, so we want to test to see, did the glass size change the selected portion? That is there a statistically significant difference between how much these two pour? So again, we're going to set up the null and alternative hypothesis. I put the large glass participants first and then the small glass participants because then that means our t-score will be positive and it's a little bit more consistent and easy to interpret. Our alternative hypothesis is just that they're not equal. Remember specifically that the problem just asked if the glass size changed how much they poured. It's not indicating direction at all, so we're just going to say that they're just not equal. So now that we have our null and alternative hypothesis, we can calculate our t-score. Again, I put the large group first and the small group second, and that's going to give me ultimately a positive t-score. If I reversed it, I would get the same number, but it would be negative. I'm going to then divide by the standard error. This is just the square root of the standard deviation squared divided by the sample size of the first group. And then again, we add for the second group that standard deviation squared divided by their sample size. That's going to give me a t-score of 2.951. The other one thing I wanted to show you was the degrees of freedom. I calculate that by adding up the two sample sizes and then subtracting 2. Now for a one sample test, we just did the sample size minus 1. But since we're dealing with a two sample, that's why we're subtracting off 2. So that's going to give me a degrees of freedom of 47. The p-value then is calculated based off the alternative hypothesis. The alternative hypothesis here being a two-tailed test. We just want to know what's the probability that we'd observe the sample that we do or something more different from 0. And so that's why we see not equal, and that's why we see 1.99, is because this is our observed difference between the two samples. This is equivalent to saying we observe the z-score that we do or something even more different from that z-score. We can calculate that probability then either using the Excel or the TI calculator that I've shown you before. Because this is a positive number, I'm going to reach up in the tail, so this is the lower bound reaching up to infinity, which is 10 to the 99th for your calculator, and then our degrees of freedom. This is a two-tailed test because the alternative hypothesis specifies it as a two-tailed test, so we times by 2. Same thing for the Excel formula. We put in our t-score, our degrees of freedom, and then 1 for the cumulative distribution function. Times it by 2 because it's a two-tailed test, and we'll get the same p-value. So based on this p-value and our alpha level, which is 0.05, we can make the following conclusion. Our p-value is less than our alpha, so we will reject the null hypothesis. We find in favor of the alternative because we have enough evidence to suggest that there is a difference between these two groups of users. That is, the glass size does change how much people pour. So that's how you run a t-test for two means. Again, I want to emphasize that the standard error is different from that shown in your book. Neither is incorrect. They're just two different methods. If you use your calculator to run these tests, it will let you choose which method you want to use to calculate the standard error, whether it's the pooled method or the non-pooled method that I've showed you here. Again, that handout that I provided for you earlier, and that I'll provide for you again in this file, will show you how to run the t-test for a two-sample means or a two-sample t-test.